All right, let's go ahead and get started. Welcome to Rhino Health's R&D Day. My name is Malhar Patel. I'm Director of Clinical Engagement at Rhino Health. First off, thank you for joining this webinar and supporting medical research in general. I'll start today by going over the agenda. First, Rhino Health team will provide some opening remarks. We'll give you an overview of the Rhino Health platform and describe how we support academic research in general. Then center stage will be passed to presenters who are presenting the interesting research projects that they have done on the Rhino Health platform. And then finally, we'll close out the session with closing remarks and next steps, because all the researchers presenting today are eager both to show you the work they've accomplished, but also to generate interest in that work and potentially collaborators too. So in other words, you, the audience, could join many of these projects and be center stage at future ones of these events. So without further ado, let me hand over the baton to Itai.
Hello, everyone. Thanks for joining our webinar and our R&D Day. Supporting academic research has been a core to Rhino's mission since the get-go. Much of the origin of Rhino is learnings from the exam study and international federated learning research during the COVID time that was published in Nature Medicine in September 2021. Our earliest users and some of the most active users of Rhino to date are researchers with over 120 research users running over 30 projects. We have supported to date over 30 grant submissions as co-submitters and providing letters of support with a total of over $100 million of funding opportunity. And some of the Rhino team members themselves are folks with background in both clinical medicine as well as academia, and folks who have published in peer-reviewed journals. In terms of the concept behind Rhino, we see ourselves as a next step in evolution and as complement to federated data and federated analytic systems. We take data that's already mapped to common data models, where you could analyze the data in order to discover and access data insights, and use our federated compute platform in order to use both federated learning as well as different usage of custom code and running fully compiled and GUI software on the edge. And with that, reaching the full usability and leverage of data. The Rhino platform itself allows developers to reach their full potential without needing to share data or compromise data privacy and ownership. We do that with a centrally orchestrated system, but execution always on the edge. Today, Rhino has active edges on AWS, Google Cloud, as well as on-prem bare metal and VMware. And so from NVIDIA GPU servers to a laptop, Rhino can accommodate whatever kind of infrastructure you have. The principles of the design and implementation of our platform are that data is stored locally and never leaves the firewall of the data custodian. Central control but distributed execution, high flexibility in terms of infrastructure, and high flexibility in terms of ways of operating the system, which is completely extensible using the Rhino SDK, and supporting of all kind of open source software for AI, data analytics, federated learning, data visualizations, annotations, and workflow. We are as well HIPAA compliant, GDPR reviewed, ISO 27001 certified, and SOC 2 certified. The Rhino network of researchers is already truly global, with a high representation in North America, representation in Latin America, high representation in Europe, and very high representation in the Middle East, in Israel specifically, as well as several locations in Korea and Taiwan. And we're growing in several new locations a month at this point. And so being part of the Rhino network really affords you with being part of a very vibrant and passionate community of researchers from around the world who are pushing the boundaries of healthcare AI. Now, I'll hand this over to Yaron Blinder, a Ph.D., our Vice President of Product, who will tell you about some of the features that Rhino has recently released in order to support the developer journey from end to end.
Thanks, Itai. Hello, everyone. Very excited to share some of the work that we've been doing recently. A few of the features that we're very excited about that we recently released, and also give you a sneak peek into some of the work that we are about to release in the near future. So first off, ever since we started working with researchers, we've received a lot of requests for implementing support for existing third-party tools. Researchers often want to continue using the tools that they're used to. Those could be annotation tools, they could be other workflow tools, depending on the type of data. And that has been a very strong focus of ours. Very excited to say that we've recently released a feature that we call interactive containers. And this enables users to deploy containerized models with an interactive graphical user interface, which they can then use on distributed data. So I'll show two of the main early examples. This first one is for a containerized Jupyter notebook. So data scientists are very used to working with Jupyter notebooks locally, but with distributed data, this is more challenging. With this new feature, users can now deploy a Jupyter notebook to the distributed data and work on it as if they were working on local data, using their own preferred tools for data visualization, machine learning, and essentially any other piece of their work. So very exciting new capability. The second example, as I mentioned, annotation tools are a big focus. Researchers often have a preferred annotation tool. So one of the first examples that we implemented is support for 3D Slicer. So in this example, there's a containerized version of 3D Slicer that is deployed on the edge via the Rhino Health platform. So it has access in a privacy-preserving manner to the data that is distributed remotely at the edge. And you can use 3D Slicer as if you were using it locally, add your annotations, add whatever additional tools you're used to using, and then import your annotations back into your Rhino Health project. So this capability drastically increases the flexibility that users have in terms of the kind of tools that they can work with on the platform. Essentially, any tool that you can containerize, you can now work with using distributed data. So here we see the full functionality of the 3D Slicer working on remote data as if you were working on it locally. Great. So the next feature I'd like to talk about is relevant to projects that have complex data that is sourced from multiple sites in the same project. So we call this distributed registries. Existing users of the Rhino Health platform are familiar with the out-of-the-box cohort analytics tool. So this enables you to have basic summary statistics of the data in the platform. So things that are already included are things like the percentage of data completeness and some basic visualizations for statistics. With this new capability, you can not only view the summary statistics, but you can also slice and dice the data to better understand, is this distributed data sufficient for what I need? Are the specific subgroups that I'm interested in prevalent in this specific data? This can be a very useful tool for external users who might be interested in a specific project and want to know, is it feasible to run my model on the data in this project? So you can see we've implemented some very nice filtering capabilities, both for numeric, categorical features. And important to say that all of these capabilities have at the basis a layer of privacy control. So subgroups that are smaller than the privacy threshold stated by the data custodian would not be exposed if the user does not wish them to. Finally, I want to move to a sneak peek of a feature that we are going to release in the near future, and that is to help users discover their existing projects. We're calling this community projects. So what you're seeing here is the projects view, where you can see projects that you are the owner of, you are a collaborator of, and this new part, which is community projects. So if you find a project in the community project that you're interested in, you can see some information about it, links, images. You can send a message to the project owner requesting to join. If you have your own project that you wish to expose to the community, you could simply publish it, add whatever links, publications, images that you think might be relevant, and basically create a community project that would then be visible to anyone with access to the Rhino Health network. So we are very excited about the capabilities that this enables our users, both for extending the network that is using their that is participating in their projects, as well as potentially using the Rhino Health platform as a repository for making data available post-publication in compliance with NIH data sharing and management guidelines. So that is it for me. I hope this was interesting, and I'm going to hand it back to Malhar for the rest of the R&D day.
Thank you, Yaron. So without further ado, I'd like to introduce our first speakers, our first research presenters, Seha A. and Umit Topaloglu from Wake Forest School of Medicine.
Hello, everyone. My name is Seha. As Malhar states, I'm a graduate research associate and PhD student at Wake Forest School of Medicine under the supervision of Dr. Umit Topaloglu. Today, I'll be talking about privacy preserving machine learning with Gerchberg-Saxton algorithm. Next slide, please. Next slide. As we know, data privacy is a critical concern in the AI industry, particularly in the field of medical research due to data sets containing PHI, and they are strictly protected under HIPAA regulations. These ethical and legal considerations have led to the adoption of various privacy precautions such as federated learning, differential privacy, homomorphic encryption, and many other alternatives in combined manner. While these methodologies have gained acceptance, their vulnerability to third-party adversarial attack during the training and the distribution of the global models to the institution for clinical usage are still a concern. To address these challenges, we are proposing an innovative alternative approach for enhancing the security. Our proposal involves utilizing Gerchberg-Saxton algorithm in conjunction with frequency domain masking. By doing so, our approach elevates the burden on the model, thus resulting in more time-efficient approach, achieving less loss on the model prediction accuracies in comparison with other alternative methods, and mitigating the concern of third-party attacks in federated learning ecosystem. Next slide, please. The Gerchberg-Saxton algorithm is an iterative phase retrieval algorithm originally designed for recovering the phase distribution of light beams. In the present day, it finds extensive use in the holographic imaging. This algorithm reconstructs the data from random Gaussian noise, preventing the local minima and maxima locations of the data distribution, which yields a more malleable approximation of the original data distribution. While the output of GS may not precisely replicate the original data, It retains the characteristic data distribution essential for efficient model training and accurate predictions. This algorithm operates alternating between spatial and frequency domain, and throughout each cycle, the phase information is maintained while the amplitude information is normalized for the future iterations. This amplitude normalization ensures a uniform distribution of the information across the data sets, allowing us to employ random frequency domain masking in the final cycle of algorithm without losing any vital information that is crucial for model training. Also, the regeneration of the data from random Gaussian noise adds an additional layer of security, preventing the reverse engineering of the algorithm for decrypting the data distribution. Next slide, please. Our proposed approach focuses on securing the training data rather than the model itself, and it's making applicable even to the models with simpler architectures. In this study, we have worked with the image data sets. Therefore, we employ a CNN model, which are well suited for handling the image data. We conduct our research using a chest X-ray, an EMRI, and well-known Olivetti phase data sets. And these data sets are publicly available under Creative Commons 4.0 license and can be obtained from public domains. Also, to test this algorithm, we have tested against 3 different adversarial attacking scenarios, including membership inference, model immersion attack, and deep convolutional generative adversarial network, or commonly known as DCGAN. Next slide, please. A membership inference attack is a type of privacy attack that aims to determine whether a specific data instance was used in the training data set of a machine learning model, more specifically identifying whether a particular patient's data was a part of training data set or not. In this slide, we compare the MIA results both on the original and Gerchberg-Saxton transform data sets across different masking settings. In the graph illustrating the results, the blue line represents the MIA's original data, while orange, green, and red lines represents the GS influence data with 0, 10, and 20% masking settings respectively. These results demonstrates that MIA predictions on the original data falls within the range of 0.6 to 7 approximately in terms of AUC scores. However, once we apply Gerchberg-Saxton, the prediction scores is mitigated and falls within the 0.5 range, which is indicating the random guessing. As I mentioned, these findings highlight a significant reduction on MIA's ability to distinguish the data, indicating the promising applicability of Gerchberg-Saxton for such attacking scenarios. Next slide, please. Next, we have the model immersion attack. A model immersion attack is another type of privacy attack that aims to infer sensitive information about input used in the training by targeting the model parameters. And the goal of this attack is to reverse engineer the inputs based on the model's output. And as shown in the results, we are achieving a gradual improvement in the protection against model immersion attack as we increase the masking percentage and achieving approximately optimal privacy at 20% masking. Next slide, please. Finally, we had the DCGAN. As most of you know, this model is primarily used for tasks of such as like data augmentation using synthetic images or enhancing the quality of images or videos. There are some instances where DCGAN can be employed as an adversary in poisonous attack. In this scenario, the attacker would require to access to the training data or knowledge about the data type used during the training. Although it's less likely to occur unless one of your contributors is the attacker, if successfully applied, this type of attack can be challenging to detect and can significantly undermine the performance of the model in desired tasks. And as illustrated in the results, Gerchberg-Saxton also provides a significant security for data reconstruction with DCGAN, even under 0% masking settings, and preventing any possibilities of poisonous attacks which are targeting the GS transform datasets. Next, please. To highlight the performance of Gerchberg-Saxton, we conducted a comparison with the differential privacy. The graph illustrates the model prediction accuracies of two identical models, where one fortified with differential privacy and the other with Gerchberg-Saxton algorithm. The red line represents the benchmark model accuracy with no privacy precautions, whereas blue lines and orange lines represents the accuracy of model influenced by Gerchberg-Saxton and differential privacy, respectively. On the x-axis, we can see the masking percentages used in Gerchberg-Saxton and epsilon values used in the differential privacy settings. And as the results indicates, the model influenced by Gerchberg-Saxton outperforms the differential privacy counterpart model in terms of prediction accuracy up to masking settings of 60%. In general, the optimal privacy level is achieved around 20% masking, as shown in the previous slides. And at these settings, we observe around 3% loss on the model accuracy in comparison with the benchmark results. Next slide, please. Similarly, we conduct the same comparison using the MRI dataset as well. These results also align with the X-ray dataset and reinforcing the consistency of model performance under the influence of Gerchberg-Saxton. Next slide, please. To provide a comprehensive overview, we'd like to talk about the cost comparison between two privacy precautions as well. For this cost comparison, we utilize MNIST dataset instead of the FACE dataset, since it's a more commonly used dataset for AI and can provide a better benchmark for comparison. To evaluate the comparison, we consider one-time Gerchberg-Saxton transformation cost, time and model training per epoch, and of course, their cumulative sum over 50 epochs. And as shown in the bar graphs, across all three datasets, Gerchberg-Saxton achieves a significant time efficiency in the comparison with the differential privacy counterpart, while further investigation and testing are required to assess its performance on different datasets. So far, we can conclude that Gerchberg-Saxton holds a promise to be an effective alternative of the existing privacy precaution approaches. Next slide, please. So far, all the results presented are obtained from local models with centralized data. To translate these experiments on federated learning environment, we are collaborating with Rhino Health team, where they have provided us with a secure and trustworthy federated learning framework for implementing these ideas in real-world clinical settings. Up to this moment, we have successfully integrated Gerchberg-Saxton in the Rhino Health platform and achieved successful transformation in the Rhino Health platform. Currently, our focus is on adapting our AI models to format compatible with Rhino Health platform. And once this step is completed, we'll test our approach using datasets showcased in this presentation, as well as we'll extend these datasets in the real-time clinical datasets to validate the effectiveness of our approach in federated learning environment. Before I end this presentation, we extend our gratitude to Rhino Health team for providing us with this sandbox environment necessary for conducting our research. Thank you for listening and participating in this wonderful event organized by Rhino team. Please feel free to email me with any questions.
Thank you very much, Seha. That was great. Next, I'd like to introduce Satish Viswanath and Mohsen Hariri from Case Western Reserve.
Good morning, everyone. I'm very happy to present some of the research we've been doing with the Rhino Health platform on federated image quality assessment. This effort being led by Mohsen Hariri in my lab at Case Western Reserve University. Next slide. So just by introduction, the team, as I mentioned, we have Mohsen, who's a research engineer in my group, who is working on developing new tools and image analytics for different applications in oncology, as well as digestive diseases. My own background is I'm in biomedical engineering, and I'm a member of the Case Comprehensive Cancer Center. So the project itself focuses on the idea of image quality evaluation. As some of you may be aware, the major one of the major challenges in machine or deep learning models is the well-known saying of garbage in, garbage out. So in other words, if you have a host of different types of images from different scanners and acquisition protocols, you may have vast differences in the image appearance, but more critically, you could also have significant artifacts, such as the ones shown over here on the right. You can have aliasing, you can have noise, you could have shading issues. These are actually existing artifacts in a publicly available cohort in the Cancer Imaging Archive for brain tumors. And typically, the only way that we really have to figure out what's going on with these data sets is to manually evaluate. Somebody has to sit and literally click through the slides, click through the images to figure out which ones are good and which ones are acceptable. And obviously, this problem is hard enough when we're dealing with data coming from a single institution. When we start looking at multiple institutions or consortium, try to get into the federated learning paradigm, it could obviously be significantly exacerbated. How do we ensure that everyone is following a consistent protocol? How do we ensure that the same guidelines are being followed to capture what is good quality versus bad quality are all significant challenges from a federated learning perspective. Next slide. So the solution that we are proposing is to try and develop an objective and quantitative assessment of image quality in a federated setting. And for this, we're actually going to be leveraging an open source image quality assessment tool that has been developed by my group, which we called Marquee, MRQY, which is publicly available on GitHub. You can see the link at the bottom over there. And this is one of Mohsen's primary foci in my group. Marquee is a very generalized open source software. The idea is to extract a series of quality measures like noise ratios or variations, as well as image metadata. And it's sort of generalized to work for any body region. So it's not specific to brain or prostate or breast. We've tested it on 6 or 7 different body regions, and it's been very usable in all of those situations. And what we've done so far, what our approach is to try and containerize this this package so that we can deploy it across all the participants in a federated network. And through the use of the Rhino Health platform, we could potentially start to build image quality models in a federated setting so that we can build better machine learning models downstream. Next slide. So the methodology so far, Marquee, which was so far only available as a standalone tool that you have to download and install on your environment, is now being containerized and is now part of the Rhino Health platform container registry. So it's accessible to users of the Rhino Health platform going forward. At this point, the study is to try and see how we can make it more accessible to users in the platform and actually run a federated image quality study. For this, the process is to try and run it on a publicly available prostate MRI dataset, which is ProstateX. And then once we are able to confirm that everyone is sort of running the tool correctly, getting the same outputs, we then plan to use Marquee on real-world multi-institutional data. So in every case, the institution has to ingest the data into its instance. The Marquee tool can be run on that dataset without us remotely being able to access the data. The local instance is able to use that data, extract the measures, the quality metrics, and look at the impact of those quality measures on the performance of AI models potentially, as well as diagnostic quality. Next slide. So this is just some sample images showing you, showing everyone here what is going on as far as the current status of Marquee within Rhino Health. So on the left here, you can see a screenshot of the interface showing you the different measures being extracted via Marquee, as well as the trends in the data in this ProstateX cohort. This is being run from within the Rhino Health platform, so we are able to deploy it and use it within that in that setting. And then just for example's sake, on the right side, we can use the measures that are being extracted by Marquee. In this case, we're using signal to noise ratio, and so the green box corresponds to images which are good quality or better quality because they have a high signal to noise ratio. And you can see there's quite a dramatic shift across this entire cohort. This is a publicly available cohort, and you can see dramatic differences across the cohort. At the far end, you have a poor quality set of images, which is shown by the red arrow. And again, you can you can see that there are differences. There are significant differences in the appearance of the image, the noise levels in the images between these. And the only way we'd have been able to do this previously is to manually evaluate it. But with the use of the quality evaluation approach, we can actually do it much more rapidly and much more effectively. Next slide. So the next steps are to leverage the established Rhino Health network to try and pursue this analysis in broader detail, including not just prostate, but potentially other body regions as well as potentially other modalities. So we are actively trying to collaborate with multiple institutions, both within and outside the Rhino Health network, to make use of this workflow. And so, as I mentioned on the slide, please feel free to reach out to us in case you have questions or you'd like to collaborate. My email is on the slide, and I believe we are already working with several institutions in Rhino Health to start to use the tool in their setting.
Wonderful.
I think that's it. All right. Thank you very much for the opportunity. Thank you all for listening.
Thank you, Satish. Next, I'd like to introduce Dufan Wu and Kevin Liu from Massachusetts General Hospital.
Hi, everyone. I'm Dufan from Mass General, and today I'm going to introduce a bit of our experience and our work on the domain shift and adaptation in the federated learning setting. It's going to be presented by me and my colleague, Kevin Liu. Next, please. Yeah, here is an introduction of two of us. Next, please. The background, we all know that the generalizability and fairness in AI is very important. And the model's performance often drops on unseen data, especially on the scanner manufacturer and the protocols. And we are also encountering this fairness of different patient populations, especially the race problem. And FAR can address these challenges to some extent. We have more data and more diversity, but we also encounter the imbalance of the data that will reside between different sites and the imbalance between the races. Next, please. We have our experience established from our previous developed brain aneurysm detection model. This background is we're trying to capture the brain aneurysm from CTA scans using AI models. It's a simple AI model with region proportional network followed by a classification network. We trained our model with patients we acquired at Mass General and tested on a local site at Federated and more than 300 patients from a non-MGB network, basically through the Rhino platform. They are distributed all over the world. Next, please. Yeah, this is our model's performance. On the right, we can see the figure shows the FROC curve. The orange curve is the model's performance on our local site. And it's the sensitivity drastically dropped when we tested on non-MGB sites. As you can see, the sensitivity almost dropped by 10%, which is quite a lot. And we stratified our model performance by sites. And it seems that it varies site by site. It's not just like we are testing on a same site, it will be bad. The model performed very well. Actually, it surpassed the performance at MGB in Cambridge Hospital at UK, where it achieved 84% sensitivity. That's because all the studies from Cambridge, they're from Siemens scanners, and we have seen those scanners in our local dataset. And the models performed the worst on the dataset from DASA. And further analysis shows that DASA used mostly Philips and Canon scanners, and where the model has never seen. So for these image-based models, it seems that the poor generalization to unseen manufacturers, this domain difference is really a very big impact. And also we can see we seem to have very large difference of number of studies from each site. Like we get so many 150 studies from DASA, but from Cambridge, due to the like the occupancy, like the local manpowers, we only get 60 studies. So these are all the factors we should take into account when we are trying to do a real FAR project. Next, please. So to address these questions, one of my colleagues, Xiao, he presented this FedR algorithm. Next, please. So our standard FL settings, we usually just equally use all the data from all the sites. We don't get any weights for all the for any of the specific domains for any of the specific site. And we also have the local settings where this is another extreme case on the second row is that we train a model for each of the sites. We will not be able to use any of the similarities of the data across different sites. These are the two extreme situations. Next slide, please. So Xiao would like to seek for something in between, which is why we present this domain-wise personalized FL, so that if we consider the real difference is not from the sites, it's mostly from maybe the scanners, maybe the protocols, and what is the resolution of the image, what is the quality of the image, as Satish has just introduced. So we would like to build a model for each of the domain, but these domains could be distributed across the sites, and our model should use both the similarity between the sites, but also could discriminate between different domains. Next, please. So this is the model we presented. This model has a shared encoder part, which maps from the image to a local feature. And based on that feature, we build different domain heads for different domains using like shown in the different color here. So this shared encoder is shared across different clients. But for the domain heads, they are different for each of the domain. So some other techniques like we reweighting all the samples based on the number, based on the count of samples per domain for fairness, and second order aggregation for faster convergence, and coupled update for stabilizing the training. Next, please. And the results here show age prediction from the face. We can see with the FedR algorithm, it has a better performance and better fairness for different races to predict the age. Next, please. And we, yeah, next, please. Yeah, and we also apply this to a COVID X-ray case, and we predict the oxygen use from the emergency room lab results and the X-ray images, and the FedR also achieves the best result across different race groups. Next. Yeah, for the conclusion is domain shift and generalization problem is one of the real major challenge in practical medical AI. Using the FL problem framework, we can somehow deal with this problem, but in balanced data still poses a problem. And domain-aware federated learning could alleviate these problems. And we are working on integrating this FedR into our FR projects through the Rhino platform, and also improve the model to handle unseen domain during the testing. I will handle the presentation to my colleague Kevin, and he will introduce some of the practical experience working with Rhino.
Okay. Hello, I'm Kevin. I'm an engineer and researcher at Chemical Lab MGH, and currently I work with Dufan on deploying models and data to Rhino. And we recently have been dedicated to deploying the brain aneurysm detection model using the video learning methods. We have made some initial progress on this, so I would like to briefly share with you guys about how we achieve it. Firstly, our researchers typically build their own machine learning or deep learning models and optimize the model's parameters through training and testing. After that, they integrate this model with the MV-Flare framework. The MV-Flare allows researchers to adapt their existing machine learning or deep learning workflow to a federal paradigm, and it enables platform developers to create a secure, privacy-preserving solution for distributed multi-party collaboration. So in other words, MVFlayer facilitates easier, safer, and more convenient feeder learning for us to use on our own models. And integrating models and related code with MVFlayer requires compliance with both NVIDIA's and Rhino's guidelines. Therefore, we need to conduct testing and debugging to ensure that our model perform as expected within the MVFlayer framework and have no configuration errors after integration with MVFlayer. Once the code passed the local test, there is one final step before pushing it to Rhino. We need to assign new input and output tasks for our models following the Rhino pass definition rules. This allows our models to correctly read various data, upload to the Rhino data server, and push the generate model data to a specific output folder. And finally, we can utilize a containerized tool like the Docker to package our project and push it to Rhino. We have spent weeks debugging this workflow since we encountered some issue with defining the input paths. We resolved them by converting the paths to absolute paths, incorporating the tubular data unique ID into the provide paths to enable the model to locate the specific data, and modifying the Docker file as well as the Docker running script to meet our requirements. So here I would like to express my gratitude to the Rhino engineering team for their kindly help. And we are now confident to say that we have become proficient in model deployment. Next slide, please. Okay, here is a feeder learning example we run on Rhino. We are currently working with Rhino UI SOO. It is easy to click and use and import our data from Rhino data server. It helps us save a lot of time on deploying models. As you can see in this slide, we basically follow a simple path on the platform from creating new schema to importing new cohort, and then invoking the model with upload. And then the model running result will be shown in the log page real quick. Like here in the right side of the slide is an example. We test our feeder learning brain aneurysm detection model on Rhino. And next slide, please. Okay, that's pretty much we have today. Thank you all for listening, and thanks Rhino for hosting this our R&D day.
Thank you, Kevin. That was great. Moving on. Next, we have Anwar and Abhi from Children's National Hospital presenting.
Hello, everyone. My name is Syed Anwar. I'm faculty at Children's National Hospital, and I'm presenting this work done with my colleagues, Abhijeet, who is a R&D engineer, and Marius George Linguraro, who is PI and professor at our lab. In the lab, we are working on developing AI solutions for pediatric healthcare. And with pediatric healthcare, we are dealing with some of the challenges when applying AI to these kids. And some of the things that I will talk about are trying to solve those problems. So I will talk about self-supervised learning and federated learning, and how we are applying this for chest X-ray. Next slide. So some background, self-supervised learning has been developed these days for many different applications, and we are looking at it from the perspective of medical image analysis. Some of the challenges that comes with this strategy is a lot of computer vision applications. They start with a pre-training that uses ImageNet, and for medical applications, if we use these pre-trainings, we have this change in domain of data because we are looking at medical images. So there's a risk of propagating biases from unrelated data sets that we are trying to handle. So what we are developing here is a domain-specific foundation model. Why it's a foundation model? Because we are training on a large data set. And once our model is trained, we can use it for many different downstream tasks. Our pre-training is on a large-scale medical imaging data set, and this is how it differentiates from other self-supervised learning where maybe it starts from ImageNet. And we are aiming to learn unique patterns and structures or textures which are present within the medical domain and within a domain-specific condition, for example, in chest X-rays. Next slide. So some of our previous work, we have developed a model which is called, which I will call as SPACERs, FL-SPCXR for self-supervised pre-training for chest X-rays. For training this model, we have used data, and the data points are more than 400,000 from public repositories. All of these are chest X-rays. We are using vision transformers as a backbone of our network. Vision transformers are these days state of the art in many vision tasks. So we are trying to adapt that for our medical tasks. But we know that these vision transformers are data hungry, so they need to be trained on a large set of data to make them work. And as I said, for pediatric conditions, in many cases, we don't have this leverage that we have this big data. So we are using this self-supervised pre-training and trying to transfer this learning from a large set of chest X-rays to pediatric data. So some of the benefits that we get here is we don't need to have labels. So we have our label-free pre-training. And the strategy is shown in this figure, where you can see the input chest X-ray. We have an image manipulation strategy where we introduce noise in the image. And this corrupted CXR is then, we train a model to reconstruct this corrupted CXR. And this is the pretest task where we are reconstructing the image as part of the pre-training. Next slide. So some more details of this strategy. So we are comparing our strategy with fully supervised learning, as we are looking for developing a method which can train even when we have limited labels or no labels available. So we do the pre-training using the chest X-ray data, and then we are evaluating our pre-training on multiple downstream tasks. This includes classification and segmentation. So some of the conditions that we have looked at are pneumonia, COVID. We're also looking at sickle cell disease and acute chest syndrome in pediatric patients right now. We are also looking at chest X-ray segmentation. Some of the results are here, and we have compared these results with some standard models that are out there with state-of-the-art performance like UNITAR, and also comparing with self-supervised learning if it's initialized with pre-training coming from ImageNet. So one result I would like to highlight here is on pediatric chest X-rays for COVID-19 detection. And we can see our pre-training strategy on a very small data set, only 200 data points, is performing very well as compared to other methods that are out there. Next slide, please. So with Rhino platform, what we are doing is we are extending this strategy in the federated learning domain. And what we are aiming to achieve with this is to have a diversity of data sources coming into our model when we train, because the data will be distributed at different sites, and we can combine the learning using the federated learning strategy. With this, we are also hoping to ensure with compliance with HIPAA rules, GDPR, and other standards, which Rhino also complies with. We are hoping to improve or reduce bias and improve model robustness across populations, and hopefully collaborate with other sites for training models without sharing CXR data. So this is our next step with Spacer and taking it into the federated learning domain. Next slide. So right now, what we are doing with Rhino platform is we are using the NV-Flare implementation and using the scatter and gather approach for training our model in the federated learning manner. In our initial data set that we have used, we have multiple cohorts. So the data come from multiple cohorts, but in our Spacer work, what we did was our training was at a single site. And we want to distribute these cohorts to multiple sites so that we can apply federated learning and see how this can be used when the data is distributed. So we plan to use Rhino platform to coordinate between cohorts and also use the Rhino platform to implement the federated learning framework. So you can see in the diagram that how federated learning spacer will be placed, data will be distributed, and then we will hopefully enable spacer for data distributed across multiple sites. Next slide, please. So what we have achieved so far. So right now, as I said, in initial training, we have data cohorts, but they are at the same site. So what we are doing, because we don't have different sites yet, so we are using the Rhino simulated federated learning option that they provide for running and developing our model. So in this scenario, we are implementing the sequential scatter and gathering approach. So right now the data is on the single site, but we are simulating the federated learning framework. And you can see on the slide that the cohorts, although residing on the same site, but are distributed. And with the Rhino platform, they are working in a pseudo federated learning manner. And then we are, so this is helping us developing the algorithm, and then hopefully we will have more collaborators, and then we can run it on distributed sites. Next slide, please. So our development is progressing. We have our federated learning spacer. We had a successful run on the Rhino platform already, and now we are planning to extend this to do some downstream tasks. This is our next task that we are going to do on the Rhino platform. Right. So to summarize and some next steps, so we are developing spacer as a domain-specific foundation model targeted for chest X-rays, and our aim is to develop this model so we can solve multiple downstream tasks using the spacer model. We want to extend this to have multiple medical centers for multiple clinical conditions. Right now, as I said, from children's, we are using some conditions that are rare. For example, the COVID dataset that we use was very small, and then also extended this to, we are right now evaluating also for TB, which is a rare condition in pediatrics. We expect with spacer and federated learning to lower the burden on data curation at a single site. And most importantly, evaluate generalization of the model at diverse sites. And with Rhino Health, we hope to recruit more or collaborate with more sites so we can integrate spacer into the clinical workflows while we test how it performs at other centers. The next slide. So if you want to contact, you have the contact information here for myself and Abhijeet. With this, I'll stop, and thank you very much, Rhino, for giving this opportunity. Thank you.
Thank you, Anwar. Thank you, Abhijeet. Next, I'd like to introduce Mathias Blom, VP of Partnerships at Rhino Health, who will be presenting.
Thank you, Malhar. Hi, everyone. Thank you for joining us today. I'm Mathias Blom, Vice President of Partnerships with Rhino Health, and I will speak a bit about a project we did together with TriNetX. Our engineers developed a concept and a feasibility study we'll walk through in some detail. So we flip to the next slide. Basically, what we did is join forces with TriNetX to demonstrate the feasibility of using federated learning and edge computing to develop prospective risk scoring models that could then be used for clinical trial recruitment on distributed data. If we skip to the next slide, I'll walk through a little bit how this worked. So basically what we did was using the database available from TriNetX, the DataWorks USA, comprising 54 or so HCOs at the time, US-based. we selected a cohort of patients, close to 1 million females with breast cancer over 18 years old that had been subject to systematic treatment in the years 2015 to 2020. These were then segmented on the Rhino Health platform into 3 separate partitions representing different geographical areas: Northeast, Midwest, and South. And as you can see, and as we'll go into a little bit in more detail next slide, all the pre-processing and data management, feature engineering, and so on and so forth was conducted in a federated manner on the Rhino Health platform, which we think is pretty novel and that can have some particular applicability to how this can be deployed in a clinical trial recruiting context. But before diving into that, I want to highlight some of the typical challenges that I think the ones of you who have tried to work with distributed data in this context may have encountered, and also on the Rhino Health platform, and the joint solution helped address them. So first and foremost, no news that there might be lack of interoperability of healthcare data. So you have like lack of structural interoperability where data may be represented in different forms, different tables, different abbreviations, and so on. But also then a semantic layer where data may not always need to mean the same thing. So even if when you're using a common data model, some of these challenges may be taken care of already upstream, as is the case with the TriNetX common data model. But then with that, when you're doing pre-processing of data, feature engineering, there are certain pitfalls that you can run into that will help address. So the Rhino Health platform lets you then do what we call cohort data analytics, which is basically out-of-the-box type analytics where you could compare statistical distributions of different variables and features across populations. And you can then also, as you see here in the line below, like if there is small sort of levels of harmonizations that you would want to do, say you would want to harmonize units of something, create features that are time varying instead of just like a regular sort of recorded observational value. You can do all of that through the Rhino Health platform, either through like custom code one-liners in Python that you could write in our central interface, or using our SDK and then push to the edge to be executed with the data remaining in place at all times. And this also extends to the more sophisticated type of data pre-processing that we'll also dig into in a bit more detail later in this presentation. Now, basically, when ingesting this type of data, observational level data, it tends to come from a number of different tables representing different features. You may have tumor characteristics stored in one table, you may have lab values stored in another, patient demographics in a third, and so on and so forth. And I think for this project we had a total of 16 or so different tables, all containing observational level data from this cohort of about 1 million. You could use these features that I mentioned before, executing custom code on the edge, to construct patient journeys from this observational data. So basically what you do is then specify ETL that could be executed on the edge that transforms those sort of disparate data points from across multiple tables and stitch them into one coherent page. And that has a couple of important implications that we'll also cover a little bit in detail later. But with that, and moving on to the next, so beyond creating the patient journeys that would allow for different types of insights that are more clinically relevant, and that also has a bearing on the way we deploy the predictive models in that context that I'll also get to later. And in addition to that, I think some of you who might have been doing data science projects in a distributed setting have also noticed that like just the feature selection to prevent things like multicollinearity, separation, and other types of pitfalls that you may encounter and that prevent models from converging or performing as they should can also be a challenge to execute on the edge in a federated setting. Our platform also supports that. We were able to develop correlation matrices, for example, that let us tease out which variables also across the different sites, and not just like for one individual site, but across the federation. One could then assess things like multicollinearity to ensure that we would cull any variables that might create problems with the model and so forth. That also extends to the topic of bias, where it shouldn't be news to anyone that sometimes institutional and even human bias gets encoded in real world data with those very concrete risks of transporting and amplifying that bias to new settings when you deploy AI. Our platform and this cohort data analytics module and other functionality also lets you very easily spot that bias, test for it using things like stratification, but also more sophisticated type of methods for bias diagnosis and detection. There's also something that we did here in order to make sure that the populations were comparable and no systematic bias was introduced or amplified as a result of this work. And then finally, when it comes to the model training, we developed AI models of different flavors of predictive models, some of them more related to deep learning and the type of neural networks that are commonly used in other domains of data science. But we also worked together with the NV-FLAIR team and using NV-FLAIR, which is the federated framework that we primarily use on the Rhino Health platform to develop XGBoost implementations, linear regression, and logistic regression, and the type of applications and AI models that are a little bit more common in this context of tabular EHR data. So if we move then to the next slide, we can cover some more detail. So I think one of the concepts that I wanted to introduce here and that I alluded to in the previous page also relates to like how this model would be deployed in practice. I think like all of you would have read these papers out there where you can predict disease progression or diagnose something, with much higher accuracy than previously was possible. And like there's a lot of precedent in the literature that shows that AI can really perform in this type of tasks, also like stratifying clinical risk. Oftentimes, I think much of those papers, they don't really consider where the rubber hits the road and where you start to think about how do you deploy this in practice and how could you really realize some of the benefits that AI makes possible. And this ties back to the data pre-processing itself. So like we sat down and thought about like how would you, if you're recruiting patients for a clinical trial, how would you typically do that? And like with many of the hospital sites and partners that would be, working with the patients and engaging them in the clinical trial, they would want to know when someone is likely to become eligible for the trial in the future, as opposed to having a retrospective lens where they would only know when someone was eligible maybe 30 or 60 days ago. So that's where the AI component comes in. And we deployed this in a way where these patient journeys were constructed at regular time intervals. I think we played around with a few different ones, but basically 30-day intervals, I think, is what we used in the end. And then when you represent the patient's trajectory with the healthcare institution as a patient journey like this, you would then have observations on, say, day 0, day 30, day 60, and so on, according to that regular cadence. What you then could do is pre-process the data. So based on that scaffold of the patient journey, as I just described with 30 days cadence, you would then construct time-varying features. You could basically, as you see here on the bottom of the page, like you could compute features like how many outpatient visits did the patient have in the last 30 days or 60 days or 90 days or whatever? What was the tumor stage at this time? All of this may vary because a patient is dynamic, right? So they would go through the patient journey and they might start at a sort of lower complexity level of disease or the less severe stage and then progress through additional stages. In this way, representing the patient journeys and time varying features also supports that. And I think this is where it ties to the deployment of the model, because when you represent the data this way, which again was conducted by us in this project with the data sitting on the edge at all times. There was no centralization of data to construct these patient journeys, but rather data sat in separate parts of the world, different servers, and we could execute this data pre-processing on the edge. But then when it comes to the deployment, this makes possible that you can basically, when you have a population at one given site or across many sites, as in this case, you can then repeatedly scan those populations with the AI model or the predictive model. And what you would then get is basically a prospective sense of the risk burden of individual patients at each site. So you can then deploy it again and again and again. And then with a monthly cadence, as in this example, you then get an updated view of how many patients would potentially be eligible for that trial, which could then be operationalized by the clinical trial recruitment teams on that local site. That would also then be close to the original data and that would never be shared across any firewalls or anything like that. So the bottom line is that the data remains in place. You can still transform it in this innovative way, deploy AI in it to get a prospective sense. Again, prospective is the key word here, of how many patients and which patients would be eligible for a trial down the line. I think then if we move ahead to the next slide here. So this basically summarizes all the key steps. Like as you see, the full arc of data science is represented here and was conducted in Federation by virtue of keeping data at rest on the individual sites in the Federation. That added some of these challenges that I mentioned before that we managed to overcome using the features we have on the Rhino Health platform in this joint solution. So basically taking it from selecting the data on the TriNetX platform, exporting the cohort, multiple disparate tables representing multimodal data, very rich multimodal data that we could then convert into longitudinal patient journeys, generate these time varying features. And I think we ended up using 30 or so in the end after culling them and assessing the multicollinearity and such. But there really is no limit to how many features you could generate in this way. It's more like about putting on your clinical thinking hat and think about what makes sense and, you know, what's the sparsest model that would still produce the performance level that you're after. Stratification, bias assessment, building the correlation matrices and undertaking that analysis that would help inform a good feature selection to make sure that the model converges and behaves as it should. And then also the opportunity here, as I mentioned, to work with different architectures, say like evaluating deep learning architectures, but also going more towards the tree-based models like XGBoost and also some of the traditional regression models and the like. And I think here there can be a nuance as well. While some of the deep learning and also say like some of the more modern tree-based approaches like XGBoost, for example, like GBM can be highly performant, there could be a pedagogical point here as well of sometimes using or at least testing some of those more conventional models as well. Even if they may be a little bit less performant, my experience is when working with life sciences customers that like being able to communicate results in the context of model architectures that they also know a lot about can be quite powerful, because those sort of more traditional regression-based models, they can provide some additional nuances and be a little bit easier to interrogate. And then when viewing them side by side with the more modern model architectures, you can get a lot of clinical insight at the sort of case level that can be very useful to ensure that you actually do not encode any bias and that you have the type of data and insights that would be most relevant for the stakeholder and of course in the end of it for the patient themselves. Perfect. All right then. So thank you so much for joining us, and I will hand it over to Malhar to wrap up.
Thank you, Mathias. Okay. Perfect. We're running ahead of schedule, but thank you to all who presented their amazing work. And I would encourage everyone in the audience who joined not to treat this as the end of a presentation, but as the beginning of a potentially highly impactful collaborative journey. As you heard, everyone who presented is eager to collaborate, and they're not alone. You saw the map on the previous slide. Innovators we work with around the world want to collaborate and want to continue pushing healthcare AI forward. So to that end, please reach out to learn more, to collaborate, and we look forward to working with you. Thank you very much.